So Lisa, a lot of Lisa Pathfinder's success can be attributed directly to the work of Martin, but also Lisa itself. Martin seems to be involved in just about everything with respect to the planning of the mission. So we're really pleased to have him here to tell us more about it.
Thanks very much, Nelson. The important thing he missed out is he's an expert in nothing. Involved in everything, but an expert in nothing. Okay, so I've got 2 slots of 90 minutes, and I'm going to try to explain how LISA works in the broadest sense. So what is it that we're trying to build? How do we make the measurements we make? How do we interpret the science performance that we get from such a mission? And if there's enough time, I'll try and describe a bit about LISA Pathfinder and what we actually did there and what that taught us. But we'll see how we get on. I'm not going to talk so much about sources of gravitational waves for LISA, but Alberto Susano is giving, I think, also 2 lectures this week, and he will talk about those things, so there's a complementarity here. Okay, so what I'm going to try to cover is the following. Why we push to lower frequency, that's pretty obvious. What's the comparison here in the low frequency range compared to the observations we do on the ground? What does that look like, and what are really the key issues? That leads us into the measurement principle for LISA. How is it we build up the measurement we make in the LISA instrumentation compared to some extent in how we do that on the ground. I'm understanding that everybody has heard lots about ground-based detectors in the last few weeks and how they work. So there'll be some parallels there. As we go through, I'll highlight various noise sources and how these come into our final estimated sensitivity. I'll talk about something called time delay interferometry in a fairly basic, rudimentary but complicated enough sense. And give you a lot of pointers to extra things you can go off and look at if you're interested. And I'll try to show you how we build up the LISA noise curve that we use for estimating science performance, and what that looks like with a few examples. And like I said, hopefully there's enough time and I can spend maybe the last 45 minutes of tomorrow's or half an hour of tomorrow's looking at some stuff from LISA Pathfinder and what it really looks like to do a space mission, which is rather different from how we do things on the ground. So I'm an instrumentalist, I think, at heart. I'm not really, as I said, I'm neither a theorist nor a data analyst nor an instrumentalist. I like everything. But so how many people here are instrumentalists? Just have a sense of. So it's not very many. Okay, so I'm I'm going to be talking to you guys. No, of course not. I'm going to be talking to everybody else. But so that's the challenge. I'm going to try to get across how the instrument works without resorting to too much math, without resorting to too much detail, to give you a sense of really what it is we measure and how it works. Okay, so you already got all of this from Nelson. There's nothing I can add there. I'm going to start here. Why we go to lower frequency. I think everybody's seen these kind of plots before, showing the kind of gravitational wave landscape that we have here. We don't have very good names for things. I think maybe we should have a brainstorming session in this thing. Think of good names for our frequency bands, but I've got small, big, and huge. So these are the ground-based detectors looking at small-ish systems, solar mass type systems. In LISA, we're looking at rather larger systems, more galactic scale, galactic supermassive black hole type systems here, and then out towards lower frequencies, potentially heavier sources, or at least at lower frequency sources with further separation. So this is usually the domain of pulsar timing, which I think Neil is going to cover. Is that right? In the next couple of days in detail. So I'm going to focus here how we make the measurements in this regime. To put that in a bit of a cleaner picture, this is a strain spectral density here of the typical noise levels we get from the observatories I'm talking about here. So I'm going to be comparing what we get in LISA and contrast that a little bit to how it works in LIGO. And there's a natural tendency as you go towards lower frequency that it's harder and harder to measure precisely the free-falling masses, which is what we're aiming to measure. Okay, and I'm going to try to talk through why that's the case and what are the details there, what are the issues. Okay, so what limits ground-based detectors at low frequency? You'll have heard all about this from the other talks. Primarily on the ground, you're trying, as in space, to measure relative motion of free-falling test bodies, test particles. And the suspensions of those on ground, because you have to suspend them on ground, they're in 1G, is partly what limits you, but really you're up against some fundamental things. You're up against all the external displacements and the noise in general on the Earth, both seismic type noise, so these are fluctuations or sources of noise which travel through the suspension that's holding your test mass. But there are also more direct forces of noise, such as gravity gradient noise, the actual motion of mass around your detector from the Earth itself can also create a force noise on the test mass. Okay. Now in space, we have similar things. We have force noises on the test masses, and we'll see that as we go through. But they can be controlled to some extent to be typically much smaller. We certainly don't have any large moving masses. That would be disastrous. So there's no Earth in the way. And the moving masses that we do have, as we'll see, are well below band, so things coming from celestial bodies. So then, because our test masses that we have in space have to get into space, they are also typically less massive than what you have on the ground. So we can't easily launch 40 kilo test masses as we have in the LIGO interferometers. Now that's force noise that's a problem at low frequencies. There are also interferometric challenges at low frequencies. Anything below sort of 10 hertz starts to become pretty dominated by structural effects due to temperature, the thermomechanical stability of the apparatus you're building. And because you start to get much larger motions, you have dynamic range issues as well, which is not something or it's something that's easier to control as you push towards higher frequencies to some extent. And because of that, you have readout noise issues, and you'll see where that comes into our estimated performance later on. By the way, I didn't say at the start, but if anybody has a question, just shout. We don't need to wait until the end or anything like that. So again, the goal, what are we trying to do? We want to measure the relative motion of free-falling test masses, and from that infer the gravitational waves passing through the detector. Okay, that's the standard bog standard thing we try to do with these types of observatories. In both on Earth and in space, this is exactly what we want. So on ground, then, this is isolation. These test masses are isolated from ground motion, allowed to be in free fall along one axis, along the axis at which you're able to make a measurement of their relative motion. And to do that, you have to do many stages of isolation to get down to the length stability you need, to get down to the point where these masses are quiet enough that compared to the length, you can measure the strain at the level you want, remembering that strain is delta L over L here. Okay, so typically there are many stages of pendulums. Each is giving you a factor of f squared, and you can chain those all together to isolate your masses into a very quiet level. So the real problem is, and I draw this specifically down to lower frequency, this is a typical plot of the ground motion in a reasonably quiet environment. This is the ground motion in our prototype hall at the AI in Hanover. And it shows you already down at these low frequencies that we're in the micrometer scale of ground motion. Okay, so if you don't isolate that, you're competing against microns of motion, and you would have to pull out signals which are, depending on the length of your detector, proportionally much smaller than this. So that's a challenge. You want to isolate that away. Here are some pictures of how this is done in advanced LIGO. You'll have seen all of these. I can skip over, but just to highlight the point again, in the design sensitivity of advanced LIGO, you see really at these lower frequencies below 10 hertz, you start to become limited by seismic noise transmitted through those suspensions. And remember, this is 10 hertz. We're talking about going in laser down to millihertz, so you can see how steeply that is rising. Obviously, it tails off at some point. The ground motion is not infinitely large as you go to low frequency. Even if you do more fancy observatories on the ground, this is a design curve, one of the many for one of the third generation observatories, ET. Even in these cases, down at very low frequencies, you're still going to end up limited by seismic noise. Okay, so the conclusion of that is then to go down to millihertz, which is where we want to be in the millihertz band. It's not really feasible to do that on Earth in a way where you can measure the length stability that we need, okay? So remember, we're looking at strains. If you remember the plot a few slides ago, we're looking for strains at the 10 to the minus 22, 10 to the minus 20, this region. So if you want to measure on ground with a baseline of kilometer, 1,000 meters, something like this, you need relative stabilities of your instrument at the 10 to the minus 18-ish level, okay? And if you're fighting against motion of the ground at micron, that's quite a lot of isolation you need to do. So to get to this frequency, we go to space. That's the idea. And so I'm going to talk about what's the measurement principle in space, because it's rather different than the way we do things on the ground-based detectors, and what are some of the challenges of these observations in space. So again, this is just to hammer home this point. Our free-falling test masses on the ground are suspended, and we're measuring along this degree of freedom where to a good approximation above the pendulum resonance, these things are free to move and therefore in free fall. And of course, we often compare different pairs of test masses, and you'll see that in particular in LISA, arranged potentially orthogonally, although it doesn't have to be, and that's usually to combat things like technical noises like frequency noise, but also to give you instantaneous measurement of other polarization, of all polarizations. So on ground, this frequency noise question plays a role also, but it's not as big of a problem as we'll see in LISA. Effectively, your laser wavelength and your clock become your ruler. That's what you're using to measure the relative motion. The wavelength of the light and the accuracy at which you know that, together with the time at which you can take measurements. But of course, because that's the case, then fluctuations in the laser wavelength, it means your ruler is fluctuating, and so you cannot distinguish frequency noise in the laser wavelength from the signal you're trying to detect. So that's a critical source of noise. On the ground, we do that by comparing the length changes in each arm, and in this case, the frequency noise is effectively common because the arms are effectively the same length to a good approximation. And so you can make yourself reasonably insensitive to frequency noise in this kind of a setup. In space, we'll see that's not so straightforward. And the other thing is that this question of length stability I already mentioned, and we looked at these numbers, I talked through these numbers before, but what you're able to do on the ground with these advanced optics, these advanced suspensions, and at these higher frequencies is really end up with a displacement sensitivity that's pretty impressive, of order 10 to the minus 19 meters per root hertz in the audio band. And this is partly achievable not only because the mirrors are very quiet, but because they are very quiet, you can hold them at an operating point. And so you can make an interferometric measurement on a fraction of a fringe, on a fraction of the wavelength, which means your dynamic range is much more under control. And in order to do that, you have to hold the mirrors to some extent. You both isolate them, but you also actively control them. But your actuation noise is all pushed down to lower frequencies. And indeed, you can see that to some extent. It's not really obvious in this plot, but this is a one noise breakdown of the displacement sensitivity of advanced LIGO, showing not totally limited by by seismic noise here, but other control degrees of freedom, it's labeled here. And that partly will be due to the fact that you're having to control your mirrors, so partly due to what we call actuation noise, and we'll see that is a problem in LISA. It's something we have to be aware of, and if we get onto LISA Pathfinder tomorrow, you'll see that that was one of our big challenges, that there is some control you need to do, and you have to make sure the force noise is kept at a good level. The other aspect that's different and challenging is that we can't do this kind of interferometric measurement where you lock on a fringe, where you control the relative phase of the two arms to a point where you're locked on a particular area of the fringe, okay, of the fringe of the interferometric fringe. Now, why can't you do that? Well, that's because we can't control the arm lengths at this level. Okay, so because of orbital motion on the free falling bodies. Remember, we've got free falling bodies. If you put those in space, they're going to follow celestial mechanics, and so their orbital motion will produce large relative motions. They are slow, but they are still very large. Okay, and you would need very active and noisy, therefore, feedback forces to maintain fixed arm lengths as you do on the ground, fixed at the level we needed. If you were to try to do that, you could probably do it by a mix of force noise. You would have to do it by a mix of force noise on your spacecraft through thrusters, and thrusters are not quiet, and through active forces on your test masses, which again are difficult to keep quiet enough. So that's all rather challenging. You can't do that, and so you can't do that kind of measurement, and instead you use a different concept. So you use a heterodyne measurement with phase tracking. That's just a technical detail to some extent, so that you can measure over many fringes. So you're always comparing the beat between two optical frequencies, okay, and measuring the phase of that beat. Okay, so I think many people have seen this little cartoon before. The idea then is to probe the relative motion or the change in proper time between free-falling masses at the ends of these arms, okay. Now obviously you can't put a test mass in orbit on its own. You need some apparatus around it to measure, and you need to shield it from all the other external forces like solar wind, solar radiation pressure, and so on. So you put those free-falling masses in drag-free spacecraft. Drag-free here refers to the fact that you don't touch the test masses mechanically, okay? The test masses are in free fall around the sun, and you follow them with the spacecraft, at least along the degrees of freedom where we make the measurement, okay? And our free-falling masses here are separated by a few million kilometers, and if you go back to the idea we were talking before about LIGO being having a fractional length stability of something like 10 to the minus 19. Here then, if we've got an arm length of a few million kilometers, 10 to the 9, and we're aiming for 10 to the minus 20, 10 to the minus 21 strain, then we've relaxed considerably how accurate our how a length measurement needs to be. And so that allows you, given the complexities of going to lower frequency, to still achieve the same relative strain sensitivity, or similar. Okay, and then the other thing you saw from that cartoon is there are multiple links here, and we'll see what we need those for a little bit later. So then this is the kind of money plot for LISA, the sensitivity curve here, expressed as characteristic strain, and I hope I'll get back to that later. It doesn't matter what that means right now, but it shows you the various kind of signals we expect to see with LISA. These are all supermassive black hole binary systems, 10 to the 7, 10 to the 6, 10 to the 5, out at high-ish redshifts. And we're able to track the evolution and merger of those systems in the band of LISA. There are many other sources on here, and Alberto Sazana, as I said, will talk about many of these things. I'm going to focus on how do we arrive at such a sensitivity curve, and what does it mean? What's behind that? A little, yeah. We'll get to that later. It's effectively because at these frequencies, your arm length, you can fit the signal wavelength in your arm. Okay, so you have nulls in there, and they're smeared out by the fact that the whole thing is moving around. But we'll come back to that later. Okay, so this is a mature concept, and you can see many evolutions of different ways this mission has been envisioned over the decades. We're back to something that looks a little bit more like this now, with 3 spacecraft with 6 free-falling test masses at the end of each of these arms, with something of the order a couple of million kilometers here separating the spacecraft, and with all the links active. Okay, and the real good news is that since what's that, last year only, it feels much longer ago, the mission is actually selected as an L-class mission on the ESA side. Okay, so we submitted a proposal for this, and I put this up just to give you the link. You can go away and read this if you're interested. It summarizes reasonably well what all the science of LISA is. The selection was last June, as I said. I have a point here to stop for questions, but I don't think there's much to discuss at this point. I'll just carry on. So coming back to these challenges then. You're trying to put a test mass in free fall, and you want to measure it with respect to another one which is millions of kilometers away, also in free fall. Okay, so these are, you're looking to minimize or shield these test masses from any external forces which push them out of these geodesic motions. Okay, those are direct competition with the gravitational wave signal you're after. As I said, you can't do this interferometry as you do on the ground. You can't use locked cavities. You can't easily do homodyne detection. We have very high dynamics here, as we'll see. We have high beam divergence between the satellites. You can't send a laser out and get it reflected back. That doesn't work, as we'll see in a moment. And so you need another kind of scheme. You need something like a transponder scheme that I'll try to describe. So, as I said, we have to shield the test masses in a spacecraft. We need to keep these local forces low enough. Okay. Of course, as you go to higher frequencies, as on the ground, these forces are the effect of these local forces on the strain sensitivity or the displacement sensitivity is dropping off with frequencies squared. That's a simple dynamics here. But the spacecraft has no mechanical connection to the test mass, and that's very important. You can only get to the level where these forces are low enough if you have no mechanical connection to the test mass. Okay, and so we need drag-free control. And another aspect, which maybe there's some time to talk about later, let's see, having a test mass in free fall isolated from the surrounding spacecraft means that it accumulates charge. Okay, it's hit by cosmic rays all the time and secondary particles from the surrounding satellite, and so its charge fluctuates in time and increases in time, and this is a source of noise which we also have to control. Okay, so in one slide then, the measurement principle, and we'll look at this in more detail over the coming slides, is like this. We make 3-part measurements. Okay, the first one is you have a free-falling test mass here. It's surrounded by a satellite, and you want to know how does this satellite move with respect to this free-falling test mass. So that's a first measurement I can do. I can do the same at the other end of the arm. Okay, I can measure the motion of this satellite with respect to this mass, and I can measure the relative motion of the two spacecraft. That's also an important aspect here. And you can see fairly straightforwardly, though it turns out not to be so straightforward, but conceptually speaking, by joining those 3 measurements together, the motion of the satellites goes away, and you're left with 2 free-falling test masses of which you have measured the relative motion. And we'll see how that works later in math while we do the TDI stuff. So what can possibly go wrong with all of that? Well, there are many things. These spacecraft are very noisy. First of all, they're shaking around at nanometers per root hertz in this band, okay, because of drag-free control, because of the thrusters that we're using to control the satellites. They're not hugely stable. Now, they're more stable than the ground, I'll give you that. But compared to the level we want to be at, they are quite noisy. And then we also have another source of disturbance. These are internal forces or relative forces acting between the spacecraft and the test mass, things of magnetic origin, things of due to thermal gradients, any kind of gradients, force gradients really, and produce motions of the test mass which you're competing against your signal. And so if you have any force gradients such as a gravitational potential here, the self-gravity of the spacecraft, and that moves, okay, the spacecraft is jittering, then that combines to make a force noise on the test mass. You're moving the gravitational potential or the electric potential that your test mass is sitting in. Okay, so that's your first problem, putting those test masses in free fall. and we'll see a lot more detail of that in the Pathfinder part tomorrow. Your second problem is that you're trying to make an interferometric measurement over millions of kilometers, which means you're shooting lasers out over millions of kilometers. So these are, you can do this fairly standard if you just consider Gaussian optics, but if you send out a laser beam with a Gaussian profile, and they never are perfectly Gaussian, but for this discussion that's okay, then you can propagate the width of the beam width, out over long distances via this formula. And if you plug all that together, this is something called the Rayleigh Range, which is a characteristic scale of the beam width. If you go far from the beam waist, the point where you produce the beam, okay, if you go far from that out to large distances, large Z, then approximately this scales linearly with the distance, and it's proportional to the wavelength of your light as well. If you plug in some sensible numbers for that in the kind of optical wavelengths we use here, so this is also similar to on ground, we use infrared 1064 nanometer lasers. If you plug those numbers in, that means by the time you've sent your beam 1 million kilometers, you've got a beam radius of 6.4 kilometers. Okay, so your first problem is you can't catch all that light, you can't intercept it, and therefore the amount, the number of photons or the amount of intensity you get is very, very low. You certainly can't reflect it back. By the time you come back again, you've got nothing left. Okay, so that's the sort of cartoon picture here. You're starting with a beam. You've got a transmit aperture and a receive aperture. In order to intercept as many photons as you can here, you use a telescope, and you need that at both ends because we send light both ways. And because you have a transmit aperture, which is your telescope, and a receive aperture, then that simple formula, you need to do some more work to estimate how much intensity you actually get at the other end. Okay, so the question is, if I send out, for example, 2 watts from my first spacecraft, how much of that power can I intercept at the other end? And it obviously depends on these apertures, and it depends on the distance. So in practice, you cannot typically send all of your light out. You've got a telescope here which clips to some extent, so you have to take that into account. And you can then, through, do I have it here? I have a horrible expression here that you can dig out. It's one of these standard cases where all of these problems have been solved by people in the 40s or the 50s or the 60s, and you recycle physics over and over again. This is a pretty old paper actually from 1970. It was done for a different purpose, but you can map it to this case where you have these 2 telescope apertures. This expression is depends on the 2 apertures you're talking about, A and B. Here for us they are the same. It depends on the distance, depends on the wavelength and other things. If you put in some assumptions here, for example, that the arm length is long compared to any of the beam properties, then there's one of the parameters here you can set to infinity. You can also set the waist to some relationship to the telescope diameter, because that's one of our controlling properties when we design the system. And you set then the annulus, these 2 apertures, to half the telescope. These are radii. And then you can consider the intensity at the far spacecraft at the distance where the distance equals the length of the arm. Okay, and so if you do all of those assumptions and plug that in, you find that your received power can be expressed as a function of the critical parameters here, which are, for example, the power that leaves the telescope, the diameter of the telescope. You have the length of the arm and the wavelength of the light, plus a functional expression which depends then on how you set up the beam in the initial case, the initial beam radius, which is expressed as a fraction of the telescope, but anyway. And so this function has a maximum, and so you can optimize this system to choose the maximum here, and you can set up your optical system to get the maximum amount of light from one spacecraft out to the other one, but approximately following this function here. Yeah. This is geometric. Yeah, this is purely the fact that I have a beam that's diverging and I intercept a fraction of the light. It's it's an effect, so there are edge effects, and that's not covered here, and they will be an effect, but I think you can see those as fairly negligible in this case. If you think about it this way, so by the time you've diffracted this beam out 1,000,000 kilometers, all the higher order optical modes are decayed to zero, and you're left with a Gaussian beam. The power that's in those higher optical modes depends on how good your initial mode is and how perfect your telescope is, and whether or not you can transmit that single Gaussian mode out. If you have other things like clipping and scattering, they will have an effect. That's not included here, but they should be small. This gives you the back of the envelope numbers of the kind of powers we're dealing with. So if I take these numbers here, if you plug in some reasonable numbers, okay, so the received power obviously depends on the intensity in the far field and the receiving aperture. It's a simple relationship. You can do that's a geometrical thing. If you plug in some numbers now, okay, here for LISA we're talking in the current baseline of 2.5 million kilometers. If I can manage to get from my 2-watt laser 1.25 watts out of the telescope, I need some light for other things. And my telescope's of the order 30 centimeters, which has some reasoning behind it as well. Then you see that my received power is in the nanowatts per square meter at the other end, which means with this sort of telescope I'm receiving a few hundred picowatts. That's not a lot of light. And that's the driver for why I cannot do any sort of cavity here. Okay, I have to pick up this light at the other end and measure it with respect to some other local oscillator, some other light field. Sure. So that's one of the optimizations one does in choosing these numbers. So you want to set up your system such that the power received at the far end, once you get it through the telescope, leaves you more or less shot noise limited to some extent. In this particular configuration, it's not quite true. It turns out there are other noise sources, and shot noise is about half of the noise power. But that's part of the optimization, yes. So you can either you can increase or decrease your telescope diameter to tune that, or change the length, but these all scale differently for that. Okay, so where are we at the moment? So we use lasers to measure relative motion of free-falling test masses, that's clear, but we can't do any sort of round-trip measurements because the received power is too low. We also can't do homodyne detection due to the large dynamic range and the fact that you can't do a round trip. And so we have to use something called heterodyne interferometry that tracks the beats between lasers. And we need to be able to detect those beats, and you'll see in a moment that's not obvious either. Okay, so what are the features of this approach? The spacecraft, the 3 spacecraft we saw in that nice picture, it looked like a rigid triangle rotating around the sun. That's not quite true. They are not totally isolated. It's not a point source sun with point source spacecraft. There are other things like the Earth primarily, but other celestial bodies that mean that the orbits of the test mass around the sun are slightly elliptical, and so the relative distance between the 3 spacecraft varies with time as the orbit progresses. That means the line of sight velocities between the spacecraft make frequency shifts on the light. I have Doppler shift of the light as I send it out. Okay, I'm sending my light from here to from the emitter to the receiver, and both the emitter and the receiver are moving relative to that line of sight. Okay, and so that's right. It would still be there because we're out of plane. Yeah, that's right. Yeah, that's right. So let's see. So we have to estimate what kind of a frequency shift we expect to get here. And this is just a standard Doppler shift formula. If you take this sort of standard setup for LISA with our 2.5 million kilometer arms, where the initial orbit or the center of the constellation is trailing the Earth by something of order 20 degrees, okay, and then each of these satellites is making this sort of slightly elliptical orbits here around the sun. The whole effect is this cartwheel effect. If you take that and simulate that, and obviously it depends on the epoch and where all the bodies are, you get line of sight velocities which are of the order of meters per second, okay, a few meters per second over the course of a 10-year mission. And those few meters a second, then you have to translate into what sort of relative frequency shifts are you going to get on the light, and how does that affect your ability to detect the beat signal. So if you convert that to Doppler shift, that results in Doppler shifts of the light you send out on the order of megahertz, a few megahertz here. Okay, so even if I had two lasers, one in this spacecraft and one in the far spacecraft, even if they had perfectly the same frequency, by the time this emitter light reaches the other spacecraft, it will have had a frequency shift up to a few megahertz, and that beat signal then between that optical oscillator and the optical oscillator at the other end, my two lasers, is what I need to be able to detect. Okay, and so this is a technical limitation. I need to be able to detect these optical beats, and when you're in the megahertz region at the noise levels we want, that's challenging in itself. But it gets a little bit worse. We need to use photodiodes to do that, and you need to track across many tens. If I go back for a second, depending on where you are, you might have relative motions that are many up to a couple of tens of megahertz apart. Given the noise levels we need and the kind of photodiodes that are available and the fact that you have to fly them in space, this is technically very challenging, and so we have to do something to control these beats to some point. We cannot let the beats, these optical beats, move outside the detector bandwidth. So we have to do something to control that, and we set up something that you can consider a transponder-like scheme in LISA. We send out one beam to the far spacecraft, so let's see, F1 here, that's at frequency F1. That's out to the far spacecraft. I interfere that with a local laser beam here, and I measure the beat, okay? If I can't measure the beat, that means it's outside my detector bandwidth, and I have to move this frequency somehow until I do detect something, and that's an acquisition problem. I'm not going to talk about that here, but let's suppose there is a beat in band at any given time. I can now lock the frequency of this laser. I can tune it to make sure that that optical beat stays in the band of my detector and in the band where I can make a good measurement. Okay, so I tune that here, the laser, this frequency F2, such that the difference between the two is detectable on my detector. And then I can send F2 back, which experiences Doppler shifts in the other direction. In this case, potentially different because the observatory is evolving. And I compare that to F1, and I have another beat here, and I have to keep those also in the band of the detector. So depending on, and we'll see that in a moment, the fact that I have 6 of these lasers, I have a full set of these conditions I have to try to fulfill. Okay, now each of these beat signals that I have here, of course, not only has it picked up Doppler shifts due to the fact that the spacecrafts have relative motion due to orbital mechanics, but they have Doppler shifts due to the fact that there are gravitational wave signals there as well. So there are many things in this beat. There are the signal we're after, which impinges on the arm. There's the relative motion of the spacecraft, which is in there. There are other things like jitter of the spacecraft, which is in there, that makes also phase shifts or frequency shifts. And there's any noise that originated at the emitter in the first place, plus any noise we have in our local oscillator here, so any frequency noises here. So all of those things end up in this signal, and we have to try and pull those all apart later on. Okay, so if you go around... Yes, yeah. They're all active all the time, yes. So this sort of shows that, let's see, if we start from here with this first laser, a laser in itself is inherently not stable enough for the kind of measurement we want to do, or at least it would impose rather stringent requirements on our ability to cancel frequency noise in TDI, which we'll see later. And so what we can do, though, is stabilize the first laser to some stable reference. That could be a cavity, an optical cavity flying in the satellite. It could be some other kind of frequency reference, depending on what you can fly here. But you can typically reduce the frequency noise of this first laser to a level by which you're confident that later in TDI we can cancel that. And without going into the detail of that, we'll see it later. So you first stabilize this guy. You send the light out. You can now lock this laser to that one, and so the relative frequency between these two is now controlled, and the fluctuations of this one are now imposed on this one. Okay, and then you keep doing that. So then you lock this one to this one, and you send its light out. You lock this one to the incoming. There are different ways to do this. You could do it in different schemes, but effectively, you lock these all together until you obviously can't lock in a complete circle. That would be that would not be possible. But you can lock more or less round so that all of the lasers are referred to as some stable reference somewhere, and you have at one point then an open end, and it's really the relative frequency of those two open ends that you end up measuring. Okay, so you have this sort of chain system. So how does this interferometry work? I guess I'm not sure how much of homodyne interferometry was looked at or whether anybody talked about heterodyne, but I'll mention briefly just a bit more detail how this works and some of the properties of this. So we're comparing two optical frequencies, okay, F1 and F2. By beating those together, you effectively get the difference of the two. You get the sum and the difference, but the sum is at very high frequencies. These are terahertz, remember, at 1064 nanometers. So I measure this beat, and the phase of that beat depends on the path length that these two beams have traveled, okay, the relative path lengths. So the interference here then, if we take a simple case, a 50-50 beam splitter, I have two light fields which I'm combining at a beam splitter. Here 50% reflective coating, perfect in every way, which of course doesn't exist. And so I sum the amplitudes of the light field here on a photodetector, and I end up making a sort of a square law detector here, because the carrier frequency is neglected throughout. It's terahertz, and there's no way that this device responds to that. You respond to the average photocurrent, which ends up making a square law detector. And so we only detect the average light fields here and the oscillation of these. Okay, so if I describe my two light fields by two simple complex amplitudes here, then my photocurrent out of this detector is the squared sum, or the square of the sum of the absolute value of these two complex amplitudes. If you propagate that out, you see that you have here some DC light power, that's a DC photocurrent, and you have some oscillatory term which is at the difference of these two frequencies. Okay, these two fields were at two different frequencies, and I have an oscillation here, and it's exactly the phase of that oscillation that we want to try to measure, because that phase here now depends on the path that these two beams have traveled. Okay, so I want to measure this phase difference. Okay, so what does that look like? If you move the beam path, so if one of the beam paths contains a moving surface, in this case a test mass or a spacecraft with a telescope, then the phase of that beam will shift relative to some reference, and it's imprinted on the relative phase that we measure in the end, or on the beat. Okay, so we mentioned frequency noise before, and it's important to look how that couples here. Because we're measuring the phase of the beat between these two laser beams, if the frequency changes, then so does that measured beat, and I can't distinguish one from the other. Okay, I mean, they're related just by a time derivative, so you can't distinguish these two things. And this little cartoon shows you that if you change the frequency of one of the beats, then your of one of the lasers, excuse me, then the beat you have also shifts in phase. So if you think of the phase as just measuring the phase angle at a given time. Okay, so that's not so good. If you shift the frequency the same in both arms, let me play that again. You see, because and they travel the same path, then the beat doesn't move anymore. Okay, and that's sort of the situation we have on the on-ground detectors. Now, okay, so frequency to phase is an important quantity. It's going to dominate the next 50 slides to some extent, and so it's important to understand what these numbers look like. So the changes in the frequency of these lasers, the fluctuations in the frequency of these lasers, couples to the output. If it's different in the two beams, as it can be, or if they travel different paths. Okay, so a simplified way to see this is that the path length difference between the two beams here, delta L, relates the frequency fluctuations to the output phase. Okay, and it's just a simple formula that you can figure out straightforwardly. So if you plug these numbers in, if you look at one end, and I've simplified this without the locking here, but if you assume F1 and F2 are at the same frequency, F2 has traveled gigameters, and F1 travels a meter. And so if they have the same fluctuations, the path length difference is now gigameters. Okay. So if you plug those numbers in now, and you start with some reasonable frequency noise, let's call it 100 hertz per root hertz in our measurement band. That's a typical number that we think we should be able to get in flight from a stabilized laser. And you plug in this arm length difference, then you end up with phase changes of kiloradians per root hertz. Okay, and if you remember, it's easy to relate the phase here to an equivalent motion through the wavelength. Okay. And so if you do that, that means that we have a noise source here, which is millimeter per root hertz. Okay, so that's quite large. Remember before we said on the ground, microns per root hertz were large. We said before that nanometers per root hertz of the spacecraft are still huge for us. And here we have millimeters per root hertz, so that's a real issue. So does that work? Well, as I said before, we're aiming for strains of order 10 to the minus 20. If your arm length is this 2.5 million kilometers, then you're aiming to be measuring distance changes around 25 picometers per root hertz. That's far away from millimeters per root hertz. Okay, so we have to do something about that source of noise. Technically in flight, there's very little you can do about it. You have to do something with the measurements themselves. Okay, so these two numbers don't match. That's not going to work. Questions up to there? Because now we're going to figure out how to deal with that. So time. All right. It doesn't matter in the end. You can't close a ring. You always end up with two ends. Or you need a stable reference that is that covers those. How many orders of magnitude was it? Oops. Well, it's something like 9 orders of magnitude. So if you have a clock that's good enough, and that means it's a couple of orders of magnitude better than the best on-ground optical clocks, and you can fly it, then you could do that. But then, in principle, you also don't need lasers anymore. You just fly clocks.
Is it also true that the two ends you're looking at are on the same spacecraft?
Don't have to be. Don't have to be. That depends on how you link the different lasers together. Is that true? It might always end up that the two... No, I don't think they have to be. I think they could be at two ends of the arm as well. Okay. So cancelling frequency noise is our task for the next 45 minutes before lunch. So the way you do that is you do synthesized interferometry on the ground. This is a concept called time delay interferometry. The basic idea is you make measurements at all the different ends of those arms, and you have enough of those measurements which you can cancel out that frequency noise. In other words, you've measured that frequency noise at multiple times and in multiple places, and by combining them, you can get rid of it in an on-ground synthesis. And we'll see how that works in a simplified way over the next wee while. So first, let's look again at the measurements. This is the same picture we've seen before. I have two spacecraft here. I have two free-falling masses. I have an optical transponder between the two spacecraft going in both directions. I have some gravitational wave signal as well. And I have two local measurements here, M1 and M2, and I can of course measure the motion of this spacecraft with respect to the reference, which is the incoming wavefront sent from this one, and I can do the same at the other side. I can take this incoming wavefront as my reference and measure the motion of this spacecraft with respect to it. Both of those obviously share some features, and that will be an important part of what comes next. Okay, word of warning. I'm certainly not the expert on this. I mean, Neil's probably the expert in the room here. But there's much literature out there if you want to look at this. What I'm going to do is simplify to get the ideas across. I'm going to look at the basic derivation to show you that it works conceptually, and hopefully you understand conceptually why it works. But there are devils in the detail all over here. I put a couple of references here. You can go off and dig those up and puzzle your poor heads to your heart's content over this stuff. It gets pretty messy as you bring in more and more realistic details, and actually we're not at the end of this whole story yet. Okay, so let's look at some notation and all of our measurements. Each spacecraft has two optical benches, simplified here and here. That's also simplifying the fact that there are lasers here. We can ignore that for now. We make no assumptions on the laser frequency noise, nor on whether or not they are stabilized together. That's not necessary for this, okay? That just helps it later, but we don't need to make that assumption at this point. I'm going to call these primed and unprimed benches. The arms are labeled opposite to the vertex, so there's a signal impinging on this arm, which is 1, it's opposite spacecraft 1, and a signal on this one opposite spacecraft 3, and 2 opposite 2, obviously. Okay. The measurements in one spacecraft, I've stolen this nice picture from one of those references 2 slides ago. If you look at the light coming in from the far spacecraft into this spacecraft, you're going to compare it against a local laser, which has some phase noise or frequency noise or equivalent displacement noise. It doesn't matter what you call it. They're all scaled relative to each other. As long as you're consistent, that doesn't matter. So I have a path here of this laser through and a path of this one, and I beat those together and I make this what we call often a science measurement or a long arm measurement, as I'll refer to it here, and we measure that beat signal. Okay, we digitize that in an ADC, and with respect to this clock, we measure its phase. Okay, and that's one of the simplifications that we're going to ignore, or one of the complexities that we're going to ignore here. The stability of this clock therefore makes a phase noise. Okay, but we're going to ignore that for now. So this is our first measurement. In a mathematical sense, and skipping out all the complexities, what have I got in here? So again, I've deliberately put no units here, okay? So however you cast these, whatever units you put them in, it should still work. Let's suppose for discussion these are all equivalent displacements, or meters per root hertz or something like that. It doesn't matter. Then I have a signal, an equivalent displacement due to my gravitational wave signal. I have a delayed version of the phase noise of equivalent displacement from, I can do this as we go along. Look, I don't need to skip this out. We have equivalent path length changes or equivalent motions due to the phase noise of the far emitter laser, but it's delayed through some delay function, which we'll talk about in a moment. I have path length changes or equivalent displacement noise in the local spacecraft due to the local laser. Okay, remember, it doesn't matter what these numbers are or if they're stabilized together. That doesn't matter at this point. I have 2 other parts, which is the phase noise on the light due to the fact that the far spacecraft is jittering, and so as the telescope jitters, it impinges or it imposes a phase noise on the light. And I have a part that's due to the local spacecraft. Okay, this one is delayed, this one is not. And then I have some readout noise, and that's a gross simplification as well. Let's just suppose that whole interferometric measurement has some readout noise. It's composed by many things: electronics, shot noise, all sorts of other couplings that go into there, but let's just call it N1 for this purpose. Okay, so that's this measurement here. It's measuring from optical bench 2 prime, which are these two terms. That phase noise is transmitted and compared to a local oscillator on optical bench number 1. So this delay, for the purpose of this simple treatment, I'm assuming that these delays are all the same length, or these arms are all the same length. They're not moving. They're all constant, and that, that's a gross simplification. And Neil is probably cringing here at this point, but it doesn't actually matter to show the concept. It changes things later if you do it all properly, but the concept is still the same. So that means that each arm imparts the same delay on the information that's traveling along that arm. Okay, that's the idea. And so you can just simplify everything by only considering one delay operator in this. If you want to do it properly, you need multiple delay operators, both directional and also for each link, all different. Okay. And so if there are multiple delays, like if I go from optical bench 1 to 2 primed and then through to 2 and then back to 3 primed, then I would have 2 delays, and I'm just going to notate that here as delay operator squared, just for the purposes of simplifying. Okay, so if you simulate that stuff, and I did that just to show you some plots, because I always like pictures of these things. If you plug in some typical numbers and you look at what you measure in this science interferometer output, here I had typical numbers for the laser frequency noise. I had typical numbers for the displacement, and I see that there's a notation problem. The red and yellow is switched. Please, I'll correct that before I give the slides out. So the displacement noise due to the spacecraft is this red bump here, and it has that shape because it's controlled with respect to the spacecraft, with respect to the free-falling mass, sorry. So it has a frequency shape in there. And then I have a noise, a readout noise, which is the yellow one, or N1 here, which is down at the few picometers per root hertz with some relaxation at low frequency. Typically, as you push things like electronics and optically stable paths down to lower frequencies, they become temperature dominated, and there's a rise in the equivalent noise level. Okay. So these are just simulated levels. If you plug all of those in, here we see this same problem again. I've expressed everything in meters per root hertz. Here we're up at millimeters per root hertz, as we said before, and we're aiming to measure down at picometers per root hertz. Okay, so I have two things in my way to get down to this level where I want to be. I'm never going to get really under this level. That's going to be a limiting noise in the end, certainly in this band. But at least I need to get rid of these two dominating noise sources. Oh, just a little bit of a side, if you want to play with these things yourself, this is how this worked, or the way I did it here. If you take some simple spectrum of a frequency noise and you simulate a time series for that, this is the kind of spectrum you might get. This is 30 hertz per root hertz here, slightly better than what I mentioned before, with some relaxation to low frequencies. Your phase noise is then just the integral of that time series, okay, which yields an equivalent displacement noise related to that phase noise that looks something like this. Okay, so this is where those millimeters per root hertz come from. If you break that down then, so my delta L over L is what I'm really aiming for. I want to be measuring down here to get the strain sensitivity I need given the arm lengths I have. So my equivalent displacement from laser frequency noise is that green line. You see that's dominating everything by far. The relative motion of the two spacecraft is dominating down here, and then I have my noise level, which I'm never going to get below my readout noise. Okay, so I need to go from millimeters to nanometers down to picometers. I have to get rid of these guys. To do that, I need some other measurements, and I have some other measurements. One is I can understand properties of my laser by comparing them to some other laser. Okay, that's always what you do. When you have no absolute reference, you start comparing things. So I can compare locally in this spacecraft my laser 1 to my laser 1 prime, okay? And I do that by comparing, so that's, let's roll back. So I have light on optical bench 1, I have light on optical bench 1 prime, and I need to compare the phase of those two. Okay, that's going to become important. There's a part I didn't mention before which introduces a complexity here. It doesn't really change the picture, but it adds a noise term. this constellation is not a rigid triangle. As the celestial mechanics evolves, the angle between the arms evolves by plus minus a degree or something like this over the course of a year. That means I need to move this optical bench with respect to this one to keep pointing at the far spacecraft, okay, slowly, but I have to do it. And that means in order to exchange light between these benches, I need to do something, okay? And one way you can do that is with an optical fiber, for example, but however you do it, you will almost certainly introduce an additional phase noise in transporting the light from here to here, okay, because you're in a mechanical system, and that's this guy here, okay? So I make this local laser, that's the same one we used before to measure with respect to the incoming wavefront, and I measure with respect to the other laser on this satellite coming in from the other bench through, in this case, a fiber, okay? That's this guy, those are the two phase noises, and this is some additional phase noise due to the fact that I have to transport this light. This looks rather similar, okay? A similar simulation here. I'm again at peak millimeters per root hertz relative phase noise of these two lasers locally. This is one of the cases where whether or not you lock or do not lock the lasers together and which ones you lock together can make a difference in this measurement. So if these two lasers are locked relative to each other, then depending on the path length, which might be of order meter, or depends how well we control it within one satellite, this noise level can be brought down significantly. It doesn't really help too much other than it eases the ability to make this measurement technically, but it doesn't matter for this conceptual discussion here. Then we have a similar reference noise here for the readout, and I have maybe noise in this backlink, in this exchange of light between the benches, hopefully controlled at the picometer level, because again, that I cannot get rid of, unless it's considered reciprocal, which is another technical discussion we will ignore for the moment. Okay, and then I have a third measurement, okay, on one bench, and that is with respect to this free-falling test mass here. So I want to measure how does this spacecraft move with respect to this geodesic test mass here, okay? So again, I have this laser light. I'm going to compare it to the light from the other bench, but this time I've bounced the light off that test mass, okay? And so now, in this beat signal, the relative motion of this optical system and that free-falling mass is imprinted on the phase of this beat. Okay, so that's this signal here, what we call the test mass interferometer. It has again the two phase noises locally in there. It has again the fact that I have to transfer the light across this optical link. And now it has another signal in there, which is the relative motion of the two bodies, which is the little delta 1 for the test mass and big delta 1 for the spacecraft. There's a factor of 2 here because I'm reflecting off the test mass, okay? So I get double the equivalent displacement for a given, I get double the amount of path length for a given amount of displacement. Okay, so and if you plug those in, you get a similar picture again, but you start to get a sense of where this is going now. I have, again, the phase noise of the two lasers up here. I have, that's this guy. I have, again, some spacecraft noise. That's this guy. And this time I managed to get the labels right. I have motion of the test mass due to local forces. Okay. Nominally, it's a geodesic reference, but it has local forces. And so this local force noise expressed here as an equivalent displacement has to be controlled, and it becomes our limiting effect, one of the limiting effects. I have no reference against which to measure that. I cannot get rid of it, so it's in competition with our signal. This one we're going to see we get rid of. This one we're going to see we get rid of. And then I have the other noises we discussed before. Okay. Okay, so then a summary for optical bench number 1, that's this guy, is these 3 measurements. Okay, and I make those continuously and in real time at some reasonable bandwidth that allows me to cover my measurement band. If you go to the adjacent optical bench and work that all out, you get a similar set of equations here. Here they're primed measurements, and there are some similarities. It's not too difficult to work that out yourself. Now you can just use cyclic permutation to roll yourself through the whole constellation in this way and write down all the equations that you have. So you have then 6 measurements on each satellite, and you have those on 3 satellites. So this is satellite number 2, and then on satellite number 3 you have a similar set. So you have this full set of equations here that you can easily now start to work with. Remember, our goal is to pull out the H's. Okay. Questions at this point? Joe?
So even if your lasers get perfect frequency, they're perfectly stabilized, you still have this problem and still would need to construct TDI combinations.
Perfectly stabilized with respect to each other or against what?
Say with respect to each other. I was just going to
Yeah.
ask if if you didn't let the lasers themselves have variation, but just consider differences in path length, would that be enough to cause problems?
It's the same. I think you cannot distinguish those two things, right?
Okay.
Yeah.
So what you're doing here is you're considering the case where you're holding the lengths the same.
Exactly.
Okay.
Yeah. Just because I don't want to introduce the complexity of those delays being time variant.
Okay.
Yeah.
You have issues with the local clocks being so different in the gravity.
Yes. That's a complexity I'm not going to talk about. But yes, we have to deal with that. We have not only are they in different gravitational potentials, they are different oscillators. They're not locked, and they have jitter, and all of that has to be taken care of on ground. Yeah, sure.
For the last slide with the combination, I was thinking about scattered light issues. I mean, since you have two optical junction, one close to each other,
Yeah.
sharing some signals.
Yes.
Is scattered light an issue, or
Yes.
you can get rid of it just with this combination?
We don't know the answer to that yet, and we don't know how it correlates between all the measurements. We are studying that, but so one thing you try to do, so you have two ways to handle that. One is you try to minimize scattered light, which at some point you can't anymore. The other is that scattered light only really matters if it scatters off surfaces which move with respect to each other. Okay.
I mean, scattered light travels to the spacecraft, to the whole optical bench, to the one close to the other, because they are exchanging signals.
Yeah, that's not so easy to. Okay, let me go. If I go here, you have to then get a scattering surface which is so well aligned and gets through, and I'm missing out all the polarization optics in here, which is another source of attenuation for scattered light. You have to get that you have to construct a scenario where that scattered light then gets into the fiber, gets out the other end, and makes it. So it is, but that's not your big issue. Your big issue is this one. You send out 2 watts here into a telescope, and some of it will come back. Okay, and a lot of it will, it might be 10 to the minus 10 of the power or something, but it's still a lot of light. And that scattered light that comes back from the telescope is in direct competition with the 500 picowatts that's coming from the other one. And that's an issue. But it's only an issue if the scattered light is not at a fixed phase with respect to this local laser, or with respect to any of the other measurements you make. So if the telescope bench separation fluctuates, you will couple the scattered light into your phase measurement. If it's constant, it will be a constant phase offset, which doesn't matter except in one particular case, in that it affects the calibration of this readout, but we don't need to go into that. So yes, scattered light is an issue. We don't know the full extent of how it will correlate in all these different TDI measurements yet, because it's very complicated to construct a realistic scenario. But we have to control scattered light levels to 10 to the minus 10 in power or something like this, or we have to control path lengths to picometers, or a mix of the two. Neil. Yes. 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 That's right. That's right. But then in that one you get other scattered light, and so it turtles all the way down. Right. One thing we can do, there's one source which is scattered light in this fiber, and one thing we can do is separate the frequency at which the scattered light has a beat from the frequency at which the other signals have a beat by using yet another laser. So there is a scheme which we probably will end up using where we have a third laser, actually two other laser frequencies to exchange light here to allow for scattering in this fiber. It adds a lot of complexity because all of that needs to be redundant, etc., 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 right? But there's a worry about these fibers, which is first they have backscatter inherently, but second, if they get hit by cosmic ray particles or if there's any kind of radiation damage, that you can generate new scattering centers, and because this is not a very stable reference, and because you don't know where the scattering points are, this is a significant source of noise, or could be. So we're actually doing hardware tests on this right now. But a mitigation of that will be to use other frequencies to separate them. Okay, so where were we? We were here. Okay, so next step. Oops. Cancelling spacecraft motion. Okay, so we had this relative motion of these two optical benches with respect to each other. That's an issue. So you're going to look at the arm linking these two benches, and we're going to see how we get rid of the spacecraft motion. And so the idea is to form a local measurement of the test mass 1 compared to the reference interferometer first of all. Okay, and just take my word for it, if you work that out, you need a factor 2 in here to maintain the relative units. So this is my test mass interferometer, this is my reference interferometer. I make this x1 measurement. I do the same at the other end, okay? And I'm going to use these two variables now. So you can form this quantity, which is you compare the science or long arm measurement in this spacecraft to the local test mass measurement and the delayed version of the far test mass to reference measurement. Okay, so you form that quantity. Remember, our science interferometer output looked like this, and we'll see why this works. So our science interferometer, we're going to subtract this guy, we're going to subtract a delayed version of this guy. Okay, and this is where my simplification about delays starts to be important, but in any case. And what you've done then, if you plug that all in, you've effectively constructed a new measurement, which is directly comparing now only a delayed version of the motion of the test mass over here to the test mass here. However, you still have some phase noises in here, and you still have a signal, okay? But my nanometers per root hertz of the optical bench and spacecraft motion has dropped out, okay? Okay, that's there. This just to show you why that works, you can plug this all in and do it yourself. If you do the same for the adjacent arm, so that was this arm, if you do the same for the adjacent arm, you form the similar combination, then you end up comparing the motion of this test mass to the motion of this test mass, again with some other signals in here. Now, cyclic permutation always saves you lots of paper here, but you know, when you do this the first time, you write it all out, and then you realize I don't need to write it all out. I believe it works. So you can do that now. You can form those quantities. You see, you just go 2'3, 3'1. You just go around the constellation. You have now 6 new chi measurements here: 1, 1', 2, 2', etc. These are all free of spacecraft motion, but they are not free of the very large frequency, the very large phase noise which comes on the unstable frequencies of your lasers. Okay, that's still there. But if I simulate that, just to in case you don't believe me that numbers subtract properly, you can make the simulation of this. You're still limited by this large phase noise, but that whole spacecraft motion is now, at least in the simulation, has dropped out with at least to numerical precision. Okay. But I still have all these other noises now all combined in this measurement, and these end up being my limiting noise sources for the final observatory configuration. Okay, now the next step you can make, and this allows you to use these time delay interferometry generators that we're going to need in a second. You need to remove some of the laser noise, and you can do that by comparing different combinations to reduce the number of sources of laser noise in your set of equations. You can form these eta measurements, which you take that previous measurement, you subtract a delayed, okay, so I need a picture here, but I don't have it. You subtract a delayed version of reference interferometer 2 and a delayed version of 2 primed. You add, so this difference here, you're comparing these two reference interferometers to get rid of the primed bench laser noises. You could equally well get rid of the unprimed ones, but it doesn't matter. You're left with then only lasers that don't have primes on them here. Okay, so I've reduced the whole problem to 3 large laser noises instead of 6. You can do that for the adjacent bench, and then, yes, you've guessed it, you do that for all the benches, and you have this new set of 6 variables, which still contain laser frequency noise here. These large beat signals here are still millimeters per root hertz. I've got all these gravitational wave signals. I've got motion of my test mass due to force noises, and motion of my test mass here, and I've got all my readout noises. Okay, I've simplified that here. There's also the readout noises from all the interferometers that I combined, but they just add up in the end. So TDI generators then take these, and I don't enter into how these TDI generators are formed or how they are derived, because that's too much for my little head in one lecture. But there's some references either in those previous slides, and I think I have some more coming up, where you can read how these are formed. But you effectively take delayed or linear combinations of delayed versions of these 6 variables and form phase noise-free measurements. Okay, that's what I just said. There are different ways of doing this. I'm not going to talk about any of them. You can go off and read these things, and I don't know if probably Neil and Joe have done these things before, or maybe if you want to talk to other people, you can do that. So this case that I've simulated and talked through with fixed equal arms is TDI 1.0. There are 3 partially correlated combinations which are free of frequency noise. They are combinations of these etas. Okay, and you see there are all these different delayed versions of these, 3 times delayed, 2 times delayed, once pure, and so on. Okay, and it turns out that if you work through these, they are free of frequency noise, and we'll see that in a second. So if I just take X and you plug in these etas here, you see that you're only using 4 of them. You're actually only, for any given TDI combination, you're only interrogating 4 test masses, and we'll see that's important in a second. If you plug all of that in and apply all of these delay operators, you get this lovely expression, which obviously is free of phase noise. This one goes out, this one goes out, and you keep going. All of these drop out because they all cancel in my simple case where all the D's are equal. Okay, and I'm left then with no phase noise now. So I'm left with a variable which has measured the gravitational wave signal many times in various delayed combinations. It's measured the motion of the test masses many times in different delayed combinations, and it's measured different combinations of the readout noise of the interferometers. So if you clean that all up, then you can see that here you've got 8 versions of the gravitational wave signal, you've got 16 versions of the test mass, and you've got 8 versions of the different combinations of readout noises. And we're going to see why those ratios are important a little bit later for estimating science performance. Okay. Yeah, it's just the time. Yeah. Yes, at different frequencies, yes, depending on the characteristic length of those delays, yes. Okay, so let's look at that a bit more. You see, if you count this up, you measure test mass 1, 1, 2, 3, 4 times, okay, and you measure test mass 1 prime 4 times, you measure test mass 2 4 times, and you measure test mass 3 4 times. So you're talking about these 4 test masses here, okay. And so what you've sort of done, or a conceptual way to think about this, is you've interrogated these test masses by sending a photon around this path and by sending a photon around this path. And if you count those up, you get these numbers, and you effectively then compare that round trip time to that round trip time, and that's your measurement. That's effectively what you've done. Mm-hmm. Yeah, that's the basic idea. Yeah. It doesn't matter how these really move. The fact that the blue and the red have traveled the same paths in the same amount of time kills your frequency noise. Yeah. Just to talk about, I don't know if you guys. So we asked at the start, who knows what a PSD is, a power spectral density? I think most people know what a transfer function is. Is that true? I hope so. Okay, I'm going to use that here because I just want to use it to talk about the response of this TDI combination. So a transfer function relates the output values of any kind of system, assuming it's linear time invariant, and you can describe it by some Laplace system. Then you can relate the input to the output by something called a transfer function. You can simplify that for along the frequency axis in a frequency domain sense by just looking at the ratio of the Fourier transform of the output compared to the Fourier transform of the input for the simplest case where you don't have additional noises. So if you take your gravitational wave signal into that horrible or very nice equation that we had earlier and look at how it transfers out, you see that for this TDI 1.0 that it transfers not flat, okay? Because you're combining all those different time delayed versions of the signal itself, you build up something which is effectively a first order derivative, okay? That means that at low frequencies your signal is suppressed. There are even points where your signal goes to 0, and you can calculate exactly what that frequency is, because in my simulation I had 8.34 seconds as the delay, just to pick a number out of the air. And so if you calculate where that first null frequency is, it's just simply the travel time. Okay, so let's plug in some noises into these things, just to simplify this a little bit and look at how these numbers start to compare in the last few minutes before lunch. So typically our readout noises are of order 10 picometers, 15 picometers per root hertz, okay, the combined total of all the readout noises. The force noise on the test mass is of the order a few femtonewtons per root hertz, okay, that's usually coming from molecular impacts on the test mass, Brownian noise, if you like. If you convert that to a test mass displacement, then it's just a 1 over f squared response plus the mass of the test mass. Here gives you an equivalent amplitude spectral density of the resulting test mass motion. So you can do that. If you plug all that in, this is with all of the noises plugged in, not just those simple numbers, but just to set the scale. Then your output x typically looks like this, and so you immediately see that at low frequencies, the thing you care about is the force noise acting on the test masses. So our observatory is limited at low frequency by how quiet can we put a test mass in free fall. At higher frequencies, our observatory, or our TDI variable, but it's true for the observatory in general, becomes limited by primarily the readout in that long arm interferometer. That's mostly due to the fact that I'm comparing picowatts to watts. So shot noise here starts to dominate. And you see all of these nulls where the response of my system for a fixed point in the sky goes to 0, okay? Okay, this is where it starts to get a little bit murky. I'm going to look if there's a good point to stop. How do I do that? I don't know how to do that. Let's keep going just for a second. To look at how that looks like in terms of a sensitivity curve, which is what you see in the literature all the time, ideally you're really working with this kind of thing. And I think when people do real data analysis, this is what they're working against. And so you rather than convert this back to strain and compare to a waveform in strain, you typically compute your waveform in this domain and compare it to these sorts of noise curves. But in order to convert this to something that's typically what we refer to in the literature, sensitivity curves, which are defined as a curve where the SNR to a given signal is 1, and they're almost always averaged over sky position, source polarization, and inclination, even in some cases. Then how do we do all of that? You need to certainly account for the fact that this TDI process has a transfer function, and that one that we just did assumed a fixed source in the sky. Okay, it's different as your antenna, as your observatory moves with respect to the source, or as your source moves with respect to the antenna pattern. Go on. Go back onto this. In this case, there's no source position in. Yes, it comes in the next step when we have to back it out. Yeah, when I have to go back to a strain curve. Yeah. So far, there's no signal. That's right. That's right. Yep, that's true. Yeah, it's only in the next step I need to care about this. So, in a picture, which is typically hard to draw, but I hope this makes a little bit of sense. I have some local strain response due to signals, let's call it in the solar system barycenter. I've got some response of my observatory to that strain depending on how it's oriented and so on. And I've got force and displacement noises. I've got phase readout in all these arms, and I've got the readout noise on my phases as well. And then I've got another transfer function which gives me a TDI output. So I've got this chain of a system, and really what you're usually talking about is not in terms of a strain sensitivity curve, doesn't include this part, so we have to back that out. I'm not going to go into the details of this, mostly because I couldn't, but you can calculate the sky and polarization averaged observatory response. If you look at this reference here, there's a derivation of how to do this. It looks something like this. And you see now, as the source frequency goes towards higher frequencies, you are less and less sensitive to it, and you have these nulls here, which, because they are averaged over sky and polarization, start to get smeared out. So I'm going to try and take that into account here in computing the typical responses you see in the literature. Okay, these numbers, I'm just going to quote, I'll give you a reference maybe at some point where these numbers come about. But basically, this is the thing we've measured at the output. We want to convert it back to something that's in strain. There are some factors into some sky and polarization average strain. So there are some factors that come in here. There's a 60-degree factor coming in because my arms are not at 90 degrees, okay? There's a factor coming in from sky and polarization averaging, which can be derived. There is a response to the gravitational wave signal from the observatory orientation and arm length and so on. And then there's the thing we measured at the output of TDI X, and there's a transfer function from signal to X, which I need to back out as well, and I have eventually the arm length, which converts my meters per root hertz into a strain. I've done this in power here, that's why things are squared, but you can do it any other way. So if you back that all out, then you get a strange looking plot like this, but just to point out in the last 30 seconds a few key features. So as we saw before, that means our derived response here now is for a fixed source point on the sky, because I've assumed some TDI transfer function for a given source on the sky. So that means that that frequency, that goes to null, and my detector noise goes high, if you like. I'm plotting this against the requirements for LISA, which are sky and polarization average, so that's why you see these nulls all smeared out. And I'm pointing out the fact that in the simulations I did here, I have slightly lower noise levels than you have in the requirements. But just to show you, that's one way to get from a more complicated TDI simulation to something that's a typical strain curve. And tomorrow we'll look at an easier way to derive this, just to do science performance type calculations. But really, when you do these things properly, you should be working in TDI space rather than in strain space. Just to finish, I'll show you, if you plug all of the noise sources in there, it starts to get very messy. But you see again, the same story again. You're limited by long arm readouts here. You're limited by test mass force noise down here. And some of the other effects start to play a role also in these frequency bands, so they're not negligible by any means. That was TDI 1.0. There are other versions of that which take into account more and more realistic scenarios, like rotation of the constellation, like varying arm lengths, time varying arm lengths, and so forth. I'm not going to talk about those. You also have to deal with clock noise we talked about, the fact that I refer my phase measurement to the wavelength of my laser and the clock at which I sample the phase. Therefore, the clock noise comes in and has to be dealt with. There are other horrible things like the signs of the beat signals switching as you deal with those Doppler shifts. You have to deal with that. There's full time varying unequal arm lengths, as I said. That backlink fiber may or may not be reciprocal depending on which way you send light through it. That has to be dealt with as well. And so here's an example of what that can look like. But typically what you have to do then is, instead of having delays squared, delays cubed, or delays to some power, you have many different delays, and they depend on the direction in which you're going as well. So that's what this typical notation looks like. You can go off and read this PhD thesis, which describes it in frightening detail. And I'll stop there for today, because it's lunchtime. But if there's any last questions, we'll carry on from that tomorrow. Everybody's hungry and tired. Okay.